When we look out at our own solar system, we see a cosmic clockwork mechanism that feels reassuringly predictable. The Earth orbits the Sun once every year. The Moon circles the Earth roughly once a month. Everything moves in neat, nearly circular paths, all traveling in the exact same direction. We have spent centuries viewing gravity through this lens of perfect harmony. But this order is an illusion. It is a local anomaly. Step outside our immediate cosmic neighborhood, and the laws of space motion begin to weave patterns so complex, so violent, and so backward that they challenge our very understanding of physics. Gravity is not just a cosmic law holding things together, it is a chaotic sculptor. And across the vast expanse of the universe, it creates structures that defy imagination. Today, we are exploring the extreme fringes of space motion. We will journey from the backward spinning moons of our own outer planets to the dark, elongated frontiers of the deep solar system. And finally, we will push physics to its absolute limit, theorizing how a planet could survive in a system dominated not by one or two, but 7 distinct stars. Welcome to the world where orbits get truly crazy. To understand how orbits can go wrong, we first have to understand how they are supposed to go right. Around 4.5 billion years ago, our solar system was nothing more than a giant, rotating cloud of gas and dust. As gravity caused this cloud to collapse, the spin forced it to flatten into a disk. Because everything in that disk was moving in the same direction, the planets that formed from it inherited that same direction of motion. They all orbit the Sun counterclockwise. This is called prograde motion. For the most part, the moons of these planets followed suit. They formed from smaller disks around their parent planets, meaning they also spin and orbit in that same forward direction. But not all of them. If you travel out to Neptune, the 8th and most distant major planet in a solar system, you encounter a massive world named Triton. Triton is a beast of a moon, but Triton has a dark secret. It is traveling backward. While Neptune spins counterclockwise, Triton orbits Neptune in a clockwise direction. This is a retrograde orbit. How does something like this happen? It is physically impossible for Triton to have formed out of Neptune's original planetary disk. If it had, the laws of physics would have forced it into a forward path. The answer is cosmic kidnapping. Billions of years ago, Triton did not belong to Neptune. It was an independent dwarf planet, wandering through the icy graveyard at the edge of our solar system. It likely traveled with a companion world. As this pair passed too close to the massive gravity of Neptune, a chaotic dance occurred. Neptune's gravity grabbed hold of Triton and violently threw its companion out into deep space. Because Triton entered Neptune's zone from the wrong direction, it was captured into a backward orbit. But a backward orbit comes with a heavy price. It is a dangerous long-term existence. When its moon orbits in the same direction as its planet spins, gravity slowly pushes the moon outward. This is happening to our own moon right now. It is drifting away from Earth at a rate of about 4 centimeters per year. However, because Triton is orbiting backward, the gravity of Neptune acts as a brake. This friction is constantly stealing Triton's orbital energy. Instead of drifting away, Triton is slowly, inevitably spiraling inward toward Neptune. In a few billion years, Triton will cross a critical line. This is the point where the gravity exerted by Neptune will become stronger than the internal forces holding Triton together. Imagine the sheer scale of this destruction. A world larger than Pluto will be literally ripped apart by gravity, piece by piece, while still in orbit. The shattered remains of Triton will spread out, forming a magnificent, bright ring system around Neptune that will rival the rings of Saturn. It will be a beautiful monument to a violent history. As we move further away from the Sun, past Neptune, we enter a vast, ring-shaped region of icy bodies left over from the early solar system. For a long time, we assumed the objects that he simply drifted in quiet, predictable, highly stretched loops. But in recent years, astronomers noticed something deeply unsettling. When we look at the most distant objects in this icy zone, their orbits do not make sense. If they were acting alone, their paths should be randomly scattered across space. Instead, they are tightly grouped together. Several of these incredibly distant worlds share orbits that are tilted at roughly the same angle. Furthermore, their points of closest approach to the Sun are all physically lined up in the same region of space. The mathematical probability of this happening by pure chance is less than a fraction of a percent. Something is actively shaping their paths. Something is acting as an invisible conductor to this space orchestra. This is the basis for the Planet 9 theory. According to advanced computer models, the grouping of these bizarre, stretched orbits can be perfectly explained by the presence of a massive, undiscovered planet hiding in the outer darkness. This hypothetical world would be roughly 5 to 10 times the mass of the Earth, locked in an incredibly long orbit that takes up to 20,000 years to complete a single trip around the Sun. What makes this orbit crazy is its relationship to the smaller objects. Planet 9 does not keep them close. Its massive gravity acts as a shepherd, pushing these smaller worlds into a stable pattern. It is a ghostly reminder that you do not need to see an object to know its orbit exists. Gravity leaves footprints in the dark, but you do not need to go to the edge of a solar system to find weird mechanics. Right in our own backyard, sharing paths with major planets, are strange objects that travel in pairs. We are used to thinking that two objects cannot share the same highway in space without crashing. But gravity allows for some incredibly creative loopholes through stable balancing points in space. These are positions where the gravitational pull of two large masses perfectly balances the energy needed for a small object to move with them. There are points ahead of and behind a planet in its orbit where objects can safely rest. Jupiter has thousands of them. They travel in stable zones, safely nested in front of and behind the gas giant, never getting closer, never falling behind. They are locked in a permanent escort formation. Even more bizarre is the horseshoe orbit. Take an asteroid that shares an orbit with Earth. From our perspective on Earth, it does not circle us like the Moon. Instead, it traces a massive, looping path that resembles a giant horseshoe wrapped around Earth's entire orbit. The asteroid takes about a year to orbit the Sun, just like Earth, but as it catches up to Earth from behind, Earth's gravitational pull gives the asteroid a little energy boost. According to the rules of space, when you add energy to an orbit, the orbit gets larger and the speed actually slows down. Because it slows down, Earth pulls away from it. Over the course of hundreds of years, the asteroid falls further and further behind, tracing the long curve of the horseshoe until Earth catches up to it from the other side. When Earth approaches from the front, its gravity robs the asteroid of some energy. Its orbit drops lower, it speeds up, and it begins to pull away again, reversing the process. It is a beautiful, endless loop where two objects share the exact same orbital lane for thousands of years, constantly playing a game of tag without ever touching. To truly understand how crazy an orbit can get, we have to leave the safety of single star systems behind. Our Sun is a lonely star, but in our galaxy, solitary stars are actually in the minority. Up to half of all Sun-like stars are part of double systems to stars locked in a gravitational dance on each other. Many others exist in triple, quadruple, or even larger star groups. When you add a second or third star to a system, the math governing orbits changes from clean, predictable patterns into a mathematical nightmare. So Isaac Newton perfectly solved the physics of two objects orbiting each other. It is simple, elegant, and stable. But the moment you add a third object of significant mass, the system becomes highly unpredictable and chaotic. There is no general mathematical equation that can predict the paths of three objects over long periods of time. The system becomes highly sensitive. A shift of just a few inches in a planet's position today could mean the difference between a stable orbit and the planet being thrown violently into the freezing void of deep space a million years from now. Yet, despite this fundamental chaos, planets do manage to exist in multi-star systems. They do it by using two specific types of stable orbits. In the first type, the two stars are very far apart. A planet orbits tightly around one specific star, treating the distant second star as a minor gravity nuisance. In the second type, the two stars are very close together, spinning around each other rapidly. The planet orbits far outside both of them, feeling their combined mass as if they were a single, central sun. This is the real-world equivalent of watching a double sunset on the horizon. But what happens when you push the system further? What happens when you add a third star? Or a fourth? Let us look at a real-world monster system located about 3,700 light-years from Earth. This system features two sun-like stars orbiting each other every 11 days. Orbiting around both of them is a gas giant roughly the size of Jupiter. Because the two central stars are constantly moving and shifting their positions relative to the planet, their combined gravitational pull on the planet changes wildly. This causes the planet's orbit to warp, wobble, and tilt over incredibly short timescales, while Earth's orbit changes by mere fractions of a degree over tens of thousands of years. This planet experiences massive, rapid shifts. If you were standing on a moon orbiting this gas giant, the path of the suns across the sky would look completely erratic. One month, the suns would pass directly overhead. The next month, they would skim along the southern horizon. The seasons would be completely unpredictable, shifting from blistering summers to chaotic, freezing winters with no clear pattern. And this is just with 2 suns. Now, let us engage in a grand space experiment. Let us take everything we have learned about stable structures and multi-star systems and apply it to an extreme scenario. Is it physically possible for a planet to exist in a system with 7 suns? At first glance, the answer seems like an obvious no. A system with 7 massive stars would generate a gravity field so turbulent, so violently shifting, that any planet attempting to weave through it would be ripped apart or thrown out of the system in a matter of years. But nature loves a challenge, and physics provides a few highly complex frameworks where a 7-sun system could actually work without collapsing into immediate disaster. To make a 7-sun system stable enough for a planet to survive, we must build a precise structure. We cannot simply throw 7 stars into a random cluster. That would lead to instant destruction. Instead, we must organize them into a carefully balanced cosmic mobile. Let us construct our hypothetical 7-sun system step by step. First, we start at the core with an ultramassive star. This star will act as the anchor of the entire system, providing a dominant, stabilizing center of gravity. Next, we introduce our first set of companions, a tight pair of smaller, sun-like stars. They orbit one another rapidly every few days. Together as a single unit, they enter into a wide, stable orbit around a central supergiant anchor. On the opposite side of the system, we introduce a second pair of stars. They too orbit each other closely, and together they orbit the central giant. We now have 5 stars stabilized in a tiered structure. To reach our magic number of 7, we take our second pair and expand it. Orbiting far outside them is another tight pair of dim red stars. We have successfully constructed a stable 7-star system. It is an intricate, tiered dance. The outer pair orbits each other. They orbit the next pair of stars. That entire 4-star cluster orbits the central giant star. Meanwhile, from the other side, the original pair of suns also orbits the giant. Systems with up to 6 or 7 stars have actually been observed in our galaxy. They are rare, but they are real. But where does the planet go? For a planet to survive in this 7-sun clockwork nightmare, it has 2 options for its orbit. The first option is the extreme outer orbit. The safest place for our planet is at the absolute outskirts of the system. The planet must orbit so far away that all 7 stars merge into a single, collective point of gravity at the center. From this immense distance, the individual movements of the 7 suns are masked by sheer distance. The planet experiences the system as if it were orbiting one single, ultra-massive star with 7 times the gravitational power. If you were to stand on the surface of this distant planet, the view would be breathtaking. In the center of your sky, you would not see a single disk of light. You would see a glittering, ever-shifting knot of stars. 2 bright suns would tightly dance on each other. Further out, another pair would trace wider paths, while a distant pair of dim red stars would cast a faint, eerie crimson glow across the sky. Because the planet is so far away, its view would be massive, taking thousands of Earth years to complete a single loop. It would be a cold, slow world, silhouetted against a chaotic solar dance. The second option is the balancing tightrope. What if we want our planet closer? What if we want it in a habitable zone, where liquid water could theoretically exist? This is where the mechanics get truly crazy. The planet would have to occupy a highly specific, highly volatile balancing point between the competing star clusters. Imagine our planet locked into a stable point ahead of the widest orbiting star groups. As the massive star groups swing through space, the planet is dragged along with them, held in place by the delicate equilibrium of competing gravitational pulls. This orbit is the ultimate cosmic tightrope. Because the stars in the system are constantly changing their positions, the balancing points themselves are not frozen. They flex, stretch, and warp. The planet would find itself in a constant state of orbit correction. The gravity tides acting on the planet would be immense. The internal core of the world would be continuously squeezed by the shifting poles of the 7 different suns. This would trigger extreme volcanic activity, cracking the planet's crust and creating massive, planet-wide oceans of lava. It would be a world defined by fire and structural upheaval, held hostage by its complex sky. What would day and night look like on a world nestled inside a habitable 7-sun system? The concept of a standard 24-hour day would be completely destroyed, depending on the alignment of the stars. The planet could experience periods of endless daytime that last for Earth months at a time. Imagine waking up to see the massive central giant star rising in the east, casting a harsh blue-white light across the landscape. A few hours later, the first pair of suns rises, overlapping each other and tinting the shadows with a warm, yellowish hue. As the afternoon progresses, the other star clusters emerge from the opposite side of the horizon. Shadows on this planet would be a chaotic tapestry. Every object would cast 7 distinct shadows, pointing in different directions, each with a slightly different sharpness and color depending on which star is casting it. As the stars move at different speeds, these shadows would dance, stretch, and merge across the ground in a fluid, dizzying display. True night would be a rare, terrifyingly beautiful event. It would only occur when all 7 stars happen to line up on the same side of the planet, leaving the opposite side facing the deep void of space. When night did fall, the sky would reveal a universe completely clear of solar glare. But this dark relief would be brief. Soon, one by one, the red stars, the yellow suns, and the great blue giant would break back over the horizon, shattering the darkness and resuming their chaotic reign. Our journey through these bizarre space parts brings us back to a fundamental truth about our universe. Gravity is not a rigid cage. It is a dynamic, fluid system capable of creating infinitely complex structures. From the tragic, doomed inward spiral of Triton to the hidden, icy choreography at the edge of our solar system, to the beautiful mathematical tightrope of sharing an orbital lane, we see that nature thrives on complexity. And when we push physics to its absolute limits, constructing intricate architectures of 7 concurrent suns, we find that even within the heart of absolute chaos, gravity still finds a way to create a delicate, stable balance. We live in a quiet, peaceful corner of the universe. Our single sun and our neat, circular orbits have given us the stability needed to evolve, to build civilizations, and to look up at the stars. But as we look out into the wider galaxy, we are reminded that our cosmic order is just a tiny slice of the pie. Out there, in the deep dark of space, worlds are dancing to a much wilder beat. They are navigating tracks that defy intuition, surviving against impossible odds, and proving that when it comes to the universe, orbits can get as crazy as physics will allow. Thank you for watching this compilation. If you want to keep exploring the deep mysteries of our universe, make sure to hit the subscribe button, leave a like, and let us know in the comments below. Would you ever want to visit a planet with 7 suns? Until next time, keep looking up.